So first things first, like we're taking some basic measurements of the arrows. Each arrow is 29.5 inches long, and we've come to the unfortunate realization that we're using an American tape measurer, and thusly it is in feet and not in meters, so we'll be doing a bunch of annoying conversions later, but for now, we're working in inches for our measurements.
Yes.
Alright, so to have a consistent draw length that we can work with, I'm going to be taping on the first arrow, and we'll be measuring for the other arrows to make sure we have a completely consistent draw length. Are you certain? A little bit earlier. Here good?
Yes.
All right. So now we're going to be using this length as our consistent length for all arrow draws. So we've already added our first piece of tape to the end of the arrow to represent maximum draw length. And now to get the actual draw length that we're going to be keeping consistent, we have to add a second layer of tape right here. Stephanie, can you grab the tape?
Yes.
So Stephanie's going to be putting tape on the other part right behind this stabilizer on the arrow. So right here is where we'll be putting the tape, and from the end of that tape to the beginning of the next tape will be our draw length, which we'll then proceed to measure and mark on the other arrows.
Since it happens,
our lovely assistant Sarah has pointed out that there is actually a marking on the arrow itself right here, which signifies where we just put our tape. That is that is where the arrow rests on the stabilizer.
Which line
at rest? We're using this line, the back line, which directly lines up with where we put the tape. So we're measuring from back line here to to the beginning of tape here to get our draw length. So we have the arrow now on here and measuring from resting point to full draw point is
17.4 inches.
17.4 inches. So before we begin the shoot that we will be measuring, we have the final measurements of string length, 167.64 centimeters, arrow length, 74.93 centimeters, and draw length, 44.20 centimeters. So what we're measuring now is anchor point displacement, which is the last of the variables we need to know before we can measure the cosine of angle B. So Stephanie's going to draw back, and we'll see how far it goes.
Okay, now pull back.
We're doing a couple of these tests to make sure that they remain accurate. Go. So now that we have our draw length and our anchor displacement and our string length, we can measure the cosine of angle B, which is one of the two angles we need to determine the final equation of W equals 2F cosine A cosine B. So to get the cosine of angle B, we need to take the draw length and subtract the arrow displacement and divide that by half of the string length. Now we're doing this because the only other way to get angle B is to measure it with a protractor, and we're already measuring angle A with a protractor, so we wanted to find a mathematical way to solve this one. This formula gives us a right triangle to solve for, and it gives us the cosine of angle B in a single number. Alright, we've just finished up the math. So to get the cosine of angle B, we're taking the draw length minus the arrow displacement over half the string length. And the math is displayed right here. Right here is the difference of draw length and anchor displacement, which gives us 24.9 centimeters. Half of 167.64 centimeters is 83.82 centimeters, which is half string length. 24.9 centimeters divided by 83.82 centimeters gives us that the cosine of angle B is 0.297. So the current process is finagling a way to measure angle A, and how we're going to do that is going to make a little quick homemade protractor right here. Take a picture using Sarah's camera, and with that picture that we've taken comparing the initial draw to the draw back, we will be able to take a rough measure of the angle that is close enough that the cosine will be usable in our equation. And now, in all of its glory, a handy little homemade protractor, courtesy of Sarah. So the basic process is going to go something like this. Stephanie's going to get her bow ready on the range. I'm going to have my finger right next to the anchor point at rest. Stephanie's going to draw it taut, and then I'm going to keep my finger where it was, and we're going to compare where Stephanie has drawn the anchor point to with where my finger representing the original anchor point was, and then compare that to the angle of the string itself to get angle A using this handy dandy little protractor. We'll then be taking that angle, taking the cosine of it, and it is the final angle to be used in our force equation. But basically the angle we're getting with the string is... It is roughly 50 degrees. Now that we finally have the cosines of both angles, we were able to do our final force equation to find the total tension force of the bow. So tension force equals bow weight divided by 2 times cosine of angle A times cosine of angle B, which is 18 pounds divided by 2 times 0.297 times 0.643, giving us a final measurement. Tension force equals 47.133 newtons. So now that we have our finalized force and we'll be deriving our velocity later, we're going to be taking some shots of Stephanie firing the arrow. Zzz. Arrows.
Almost right on the animal.
Whoa, dang.
Well, over the head too.
Alright, so then, once he's clear, we'll retrieve the arrows because I can't walk out there with people firing. Alright, so now Julian's gonna give his shot. Ha ha ha. No, who am I kidding? Alright,
That
and
actually went really well.
that actually did pretty well.
I actually hit the target pretty efficiently.
Can you see the arrow? It's to the left of the monkey. And by the leg, right there. Not bad.
And that concludes our demonstration on the physics of archery. If you have any questions, we'll be free to answer them.